Okay, now we have here chapter 4, part 2, neutralization reactions with gas formation. So when we have a carbonate or bicarbonate react with an acid, the products are salt, carbon dioxide, and water. For example, here we have a calcium carbonate react with a hydrochloric acid and making calcium chloride, that is a salt, and also make carbon dioxide and water, right? Then next we have a sodium bicarbonate react with this acid, and it also will make a salt, that is the case, sodium bromide, and carbon dioxide and water, right? Next we have here this reaction here as a double replacement reaction. And is also, this one is making the sodium sulfide react with sulfuric acid, is making sodium sulfate and hydrogen sulfide. So, and then when we have sulfide here, right? The sulfate is a SO4 here. When you have oxygen less, we change from H to I. So strontium sulfide react with an acid, will make a salt, sulfur dioxide, and water, right? This is also different kinds of neutralization reactions. That in the ending of chapter 4, part 1, we saw this reaction here. So these neutralization reactions that you can see here. This neutralization reaction, and when you have a strong acid, a strong base, will make salt and water. This is a neutralization reaction also, right? So the next type of reaction we have is a redox reaction. Redox reactions, they have oxidation and reduction. So redox reactions are reactions that involve the transfer of electrons from one reactant to another. So in a redox reaction, we have oxidation and we have reduction. One will not happen without the other, right? Here. One cannot occur without the other. So the term redox, reduction, and ox for oxidation. So, but what is an oxidation? Oxidation is loss of electrons. So oxidation, we can try to help you to remind, oil is oxidation is loss, right? Oil, oxidation is loss of electrons. And then we have the gain, reduction is gain of electrons. So we can try to remind you about reg R is reduction. So reg is reduction is gain. of electrons. So for example, here we have an example of a redox reaction with calcium reacting with oxygen, making calcium oxide. So how do you know about which one is oxidizing, which one is reducing? So we needed to track the oxidation numbers. So in the reaction rule is to understand about oxidation numbers, right? To recognize. So calcium. Calcium is an element, right? There is no charge here. It's just one element, like by itself. So the oxidation number is 0. So the elements in this elemental form will be oxidation number 0. As well as oxygen gas. Oxygen gas here is just O2, just oxygen with oxygen. There is no charge here, so oxidation number is also 0, right? Then we have calcium oxide. Calcium oxide. Calcium is in the group 2 periodic table, so 2 plus. So the elements in the group 1 periodic table will be 1 plus oxidation number plus 1, and the 2 plus, or plus 2. And the oxygen is the group 6A periodic table. And usually the oxygen will be oxidation number going to be -2. Okay. So, and that makes sense, right? That's correct, because also there is no charge here, right? Calcium oxide, the net charge is 0. So we have here the oxidation number. Oxygen is -2, and calcium is a +2. Okay, so let's go here, right? Calcium +2, oxygen -2. Okay, let's track the oxidation number. So calcium was initially 0, and it changed from 0 to +2 right here. Calcium oxidation number changed from 0 to +2. If it changes to 0 plus, from 0 to +2, it is losing or gaining electrons. So electrons are negative, right? That means if the number increases here, that means you are losing electrons. So that means calcium lost, that is the case here, from 0 to +2, actually lost 2 electrons. If calcium lost electrons, calcium is being oxidized, right? We saw in the previous page that oxidation is loss of electrons, correct? Okay. Now let's track oxidation number of oxygen. Oxygen here changed from 0 to -2. So from 0 to -2, right, is gaining electrons. If it's gaining electrons, oxygen here is, you have a reduction. Reduction is gain of electrons. Oxidation is loss, right? So you can see here. The calcium solid is oxidized, losing electrons here, right? The calcium is losing electrons, and the oxygen is gaining electrons. So calcium is oxidized, and oxygen is reduced. Oxygen is reduced here. And combined, they will have these two ions, calcium 2 plus, oxygen 2 minus ions. Okay, then we have here examples of redox reactions. The first one, we have a combination, right? We saw in chapter 3 about the types of reactions, like combination, the composition, right? So combination is also synthesis. It's a reaction when the reactants combine into one compound here, right? Okay, now let's track it here. The aluminum, right, is just the element aluminum here, no charge, so the oxidation number is 0. The same thing for oxygen here. The oxygen here is just the oxygen with itself, it's in its elemental form, so oxidation number is 0. Okay. And the oxygens, the usually oxidation number for oxygen is -2, right? Okay. Let's say that you don't know aluminum oxidation number. So, okay, let's find a way to calculate this oxidation number. So let me write it here. What's the net charge for this compound here? Are you seeing any charge? No, right? That it means the net charge is a 0 here. Okay, for oxygen, you know that will be a oxidation number going to be a -2. Aluminum, we don't know yet. Let's call X. Right? Now, let's make the math now. 2 times X. So X -2 times 3. -6. So we'll know that X will be equal to 6 divided by 2 will be 3. So the oxidation number for aluminum here will be a +3 here. Right now, let's check which one was oxidized, which one was reduced. So have it here, aluminum here, right? Changing from 0 to +3. So when the number is increasing, you are losing electrons. If you are losing electrons, you have oxidation, right? And then the oxygen number here, oxygen is initially 0 and changing from 0 to -2. So when the number is decreasing, is reducing, you have a reduction. And reduction is what? Is gain of electrons, right? So when the oxidation number decreases, you have your reduction. And reduction is the gain of electrons. Remember that electrons, right, they are negative charge. That's why gaining when the number are decreasing is because you have a gaining of electrons. So decomposition is also a kind of redox reactions. Here, right, have one reactant splitting into 2 products. Is also the oxidation number will also change in here. So if the oxidation numbers are changing, then we have a redox reaction. Single replacement reaction, we have, right, single displacement is when we have just one trait. Aluminum react with water, we will make aluminum hydroxide and hydrogen gas. So the oxidation number for aluminum, right? The elemental form of aluminum is 0. For the water, oxygen is usually -2, and the hydrogen is usually a +1. So then let's track here. Aluminum group 3 plus, and also is group 3A, so usually going to be a +3. So aluminum changed from 0 to +3, so the number decreased, so that it means lost sorry, the number increased, right? If the number increased, we have oxidation. Oxidation is loss of electrons, correct? Okay, oxidation is loss. Oil, try to remember this, oil. Oxidation is loss of electrons. So then you have, so hydrogen is just hydrogen by itself, right? It's elemental form, so oxidation number is 0. So hydrogen here changed from +1 to 0. The number decreased. The number decreased, the number reduced, we have reduction. And reduction is gain of electrons. So all these kind of reaction here, they are examples of redox reactions. The oxidation numbers are changing. In a redox, we have reduction and oxidation. So one will not happen without the other, because one side will be losing electrons. Now notice one will be gained. So you need to have the oxidation and reduction in a redox reaction. Okay, but how to find the oxidation, how to find out if an oxidation reduction reaction has happened. So we need to understand about some rulings first. We need to track the numbers of the oxidation numbers. So oxidation numbers are assigned to each element in a neutral compound or charged entity. So rule is for assigning oxidation numbers. The atoms in the elemental form have oxidation number of 0. This is what I talked about, right? Here, like this one. The oxidation number of monatomic ion is the same as its charge. For example, here, what's the oxidation number for the ion, this chloride ion? That's one minus here. The oxidation number here will be -1. So the oxidation number of monatomic ion is the same as its charge. Non-metals usually have a negative oxidation numbers, although they sometimes can be positive. Like oxygen is usually -2, except when it's the peroxide ion, where it will be -1. And hydrogen is usually +1 when bonded to a non-metal, but if hydrogen is bonded to a metal, it will be a -1. And fluorine and the other halogens, that usually -1, unless when combined with oxygen, so they will be positive. Okay. So single replacement reactions, also known as displacement reactions, right? You have just one trait For example, here, hydrochloric acid react with magnesium. The magnesium here will be now with the chlorine, and hydrogen now will be by itself, right? So single replacement reactions, ions oxidize. The ions oxidize an element, and the ion is replaced in solution. So the magnesium replaces the hydrogen here, right? Magnesium replacing the hydrogen is what's happening here. So can all single replacement reactions happen? Meaning, can any solid metal displace the metal cation in a compound to perform a single replacement reaction? The answer is no. The answer is depend. It depends. So how do we know which ions will occur? So I have this table here. So elements higher on the activity series are more like here, right? They are more reactive and more easily oxidized. So that means we lose electrons to exist as an ion, right? So here, the elements lower on the activity series are less reactive and more easily to reduce. So if we reduce, we'll gain electrons to exist as the element. All right. Okay, so let me see the next topic here. So we have here this table, right? So easy to oxidation here, with the guys on there. Higher, the elements higher here are more easy to oxidize. And the guys here in the top bottom, they are more easily to reduce. So a metal element will only be able to replace another metal, cation, if it's higher in the activity series than the metal cation in the compound. So depends on the location, right? If the another metal is higher than the metal cation, then is when we'll be able to replace. The next page. So the next here you have molarity. Molarity is a concentration of a solution. The quantity of solute dissolved in a solution is called the concentration of the solution. So in molarity is 1 to measure the concentration of solution. And the formula for molarity is moles of solute divided by the volume of solution in liters. So we need to pay attention. If the volume of the question is given in milliliters, we need to convert it to liters. And from milliliters to liters, you divide by 1,000. Because each 1 liter has 1,000 milliliters, right? Okay, so these formulas here, you need to memorize. So molarity is moles of solute divided by volume in liters, volume of the solution in liters, and mole is mass in grams divided by the molar mass. And molarity can also be used to convert between moles. Molarity can also be used as a conversion factor between moles and liters. Okay. Right, then The next, here you have mixing solution. How to create a solution? Like you have a molarity, right? How can you make a new solution? How can you do this step here? The first step, determine the desired molarity for a given aqueous solution and how much volume of the aqueous solution is needed. So first needed to know the molarity, right? And volume in liters, right? So once you know, you can solve for the moles of the substance and the molarity equation. So once you know the moles, you can use the molar mass of the substance, right, to calculate the mass in grams that will need to be weighted out to make the desired concentration of the solution. First thing, we calculate the mass, right? So weigh out in a known mass of the solute that will be dissolved in the solvent. Then add solute. Let me show the picture here. Right here. So first thing, right, you need to calculate how much you need. You need to calculate the mass, right? So once you know how much you needed, you're gonna add out the calculated amount here, right? And this solid here will be dissolved in water. So you want to add the solid to the volumetric flask here, this example here. And then I'm going to add water until the desired volume. Add solvent here. Add solvent until it's healthy filled. And then seal the flask, the volumetric flask, with the stopper and mix. By turning the flask upside down, right, like this, multiple times until it looks all dissolved. So after it's all dissolved, then you take off the stopper and continue adding solvent until the line. Like, for example, this flask here is at 250 milliliter. So you have a mark that says that it shows here where we should stop. Step 5, take off the stopper and continue adding solvent to the line of the neck of the flask. So place the stopper on top and seal to seal the volumetric flask and mix by turning the flask upside down and right side up again multiple times. How you make a solution. Okay, so then you have, but how we can calculate how many grams do you need to make a solution, right? So we need to know the molarity, that's the concentration, and the volume, right? Here. For example, what's the formula for molarity? We need to memorize this formula. Molarity is N, that's moles of solute divided by volume in liters. In liters, right? Okay. So let's find the moles. You needed to calculate for this case here, right? You need to find the molarity is given 0.500 molar, and the volume is given 0.350 liters, correct? Here. So If you rearrange it, molarity is equal moles times volume. So molarity is equal moles divided by volume, right? So you can do like moles will be equal molarity times volume. Moles will be molarity times volume. Molarity was given 0.500. Volume was given 0.350 liters, right? So let's multiply here. When you do this multiplication, you find the moles numbers. 0.175 moles, right? The question is asking for how many grams, right? So we need to convert from moles to grams. So we saw in unit 1, right? How do the conversion from moles to grams? Right? From moles to grams, you are going what? From moles to grams, we are going to multiply moles by the molar mass. So what's the molar mass of sodium sulfate here? Right? The molar mass is 142.042 grams per mole. This is the molar mass of sodium sulfate, right? So then let's multiply. So, okay, the mass will be equal to what? Moles times molar mass, right? So what are you going to multiply? The moles that was calculated here. Calculate 175 moles times the molar mass, 142.142 grams per mole, right? Okay. This example of the question to calculate the grams, right? If the question gives the volume and molarity. Okay, so the next problem here is to calculate the molarity. So the question gives the mass, gives the formula, because if you have the formula, you can calculate the molar mass, right? And it also gives the volume. So let's go here. Molarity is molar mass. Oh, sorry. Molarity is moles divided by volume in liters, right? Molarity here. Okay. So let's calculate the moles here. You needed to have moles, right? But to calculate the moles, what do you need to calculate mole numbers? You needed, so the moles is mass divided by molar mass, right? Okay. So the mass given was 23.4 grams, and the molar mass that's the same. You saw here that's 142.044 grams per mole. Divide one by another one here. You have your unit in moles. Now that you have your mole here, we're going to divide it by the volume. The volume given was 125 milliliters, right? But you cannot use it in milliliter, you need to convert to liters. How do this conversion from milliliters to liters? Divide by 1,000, right? So 125 milliliters divided by 1,000 will be 25 liters. All right. All right. So to divide the point, 165 moles divided by this volume here, you have this molarity. Okay. All right. So just to let you know, this portion here is from the question above here. Because not to have room here to finish, so I answer this portion here. So for question 15, it's to here. All right. Okay. All right. Okay. So let's go to the next topic that is about him. Okay, here. So if you already have an equal solution in a concentration, and you'd like to obtain an equal solution with the same solute and solvent, but at a lower concentration, you can perform a dilution. So a solution can be diluted by adding only solvent. So that means we will increase the volume of the solution, right? And the concentration will be lower. But the moles do not change. Okay, so the moles not change because the mass will not change. The only thing that will be changed will be the volume and the concentration, right? So molarity is moles, right, of solute divided by the volume of the solution in liters. Okay, let's say that initially you have a solution, it's 1 molar solution here, 1 molar. And need to make another solution. The only solution that you want would be like, for example, 0.100 molar, right? So it will be, this is the initial concentration, this is the final concentration. Okay, so let's draw, take 25 milliliters of this 1 molar stock solution, and let's add here the second volumetric flask. So adding the concentrated solution into this flask here, the total volume is 250 milliliters, right? Right, and now after you add this 25 milliliters from this solution to this flask, now we are going to complete adding water until the mark. Until the volume. The volume of this flask is 250. That means this mark, when the volume you get in the mark here, the liquid gets here in the mark, that means is when we achieve the volume. In that case, 250 milliliters. So the formula to calculate dilution is MCVC equal MDVD. C for concentrated, D for diluted. For example here, right? So CVC equal MDVD. So the example here. What was the molarity of the solution? Was the stock solution, the initial solution here will be 1 molar, right? Times volume. What was the volume that was taken here from the initial concentration was 25. So times 25 milliliters. Equal to, let's say that you don't know what is going to be the final concentration yet. Let's see. Let's solve for MD. And VD, that's the final volume. The volume of the diluted solution will be this number here. Right? So we are going to solve for MD. So MD is equal 1, right? 1 molar times 25 milliliters divided by 250 milliliters. The concentration of the diluted solution will be 0.100 molar, right? Don't forget the unit. They have it here. The formula to calculate diluted solution is MCVC equal MDVD, and some books also will be M1V1 equal M2V2, or M initial volume, initial, and here for final and final. So after you added the water, we're going to again add water up to the line here and mix thoroughly. Then you have your new solution. Right, okay. Right, oops. Okay. So have here another example. So how many milliliters of 3 molar sulfuric acid are needed to make a 450 milliliters, so the final volume, right, of 0.10 molar sulfuric acid. So the final concentration and final volume, right, he will be the diluted concentration that we're going to see. That's your final concentration here. So MCVC equal MVVD. The question is asking how many milliliters we need to take from this concentrated solution. So let's go. MC is 3 molar. The volume we don't know yet. MD is the molarity of the diluted solution, and the final volume is 450 milliliters. And do this division here, do this multiplication and divide by 3, right? After rearranging here, so for the volume for BC, you are going to calculate it here. Now, pay attention to the correct number of significant figures. So here you have 3 molar, have only 2. 450, you also have only 2, right? Because the 0 here, there is no decimal point. So the 0 here, this here, this 0, you do not count. But here you also have 2. You also have 2. So the math here will be 15 milliliters with only 2 significates, right? 15 milliliters. Okay, so one thing to pay attention here. So if you are diluting an acid, right, like this one, the sulfuric acid is a strong acid, you are going to add acid to water. This AA to W means here is add acid to water. Not the opposite. All right, okay. So next topic here is about, oops, let's the resolution get better. Okay. Stoichiometry and aqueous solutions. So we saw stoichiometry in chapter 3, right? So now let's go back to stoichiometry now. Right. So we saw in chapter 3 that from grams of A to grams of B, you need to go for all these steps. So grams of A to moles, you are going to divide by the molar mass. And to convert it from moles of a substance A to moles of a substance B, you are going to use the coefficient from the ballast equation, right? And after, when you finally find the moles of B, you are going to multiply by the molar mass to find the grams of B, right? So from grams to moles, you divide by the molar mass, and from moles to grams, you multiply the moles by the molar mass. Okay. So now, how go from moles to particles? From moles to particles, you multiply, right here. You multiply by Avogadro's number, right? Because each 1 mole of any particle is equal to Avogadro's number. Okay, but what now is about solutions? Now that you are talking about solutions, you also can use the solution to find moles. For example, if you have the molarity and the volume, so the concentration, so the molarity and the volume in liters, if you multiply the molarity times the volume, you can find the moles. And you also can use the moles of molarity to find the volume. All right. We're almost done here. Mm. Let me pause here. Okay, the next stop here, the last one is about titration. Titration is an analytical technique in which one can calculate the concentration of a solute in a solution. For example, here, so you have an Erlenmeyer with a sample that you don't know the concentration yet. For example, here, you have 20 milliliters of acid solution was added to this Erlenmeyer flask. And then you add a few drops of the acid-base indicator. So the indicator will change the color when you achieve the end point. Is when will stop, right? And then we have the burette. The burette, you are going to add your solution. Like example here, you are going to add standard sodium hydroxide solution in the burette. You are going to read, okay, what's your initial volume? So there's burette here, and we are going to draw, so we have this Erlenmeyer here, right? With your acidic solution, you don't know the concentration yet. The only thing that you know here, for example, is the concentration of sodium hydroxide. So a solution of known concentration, the standard solution, It's usual to find the concentration, the unknown concentration of another solution. So we don't know this yet, but we know sodium hydroxide concentration here. So we are going to let drop by drop here until change the color. The color using, so the solution becomes basic when past equivalent point and will be showing by the color here. So let's see. The reaction is complete at the equivalence point is when we are going to stop here, which is based on the seen endpoint. So endpoint is when the color changes. The endpoint will be, we're going to choose an indicator that it has about, the indicator will change the color in the area, the volume close around to the equivalence point. Equivalence point is when the moles of the known and unknown, they are equal. The moles of the known solution and the unknown solution, they are equal. Is the equivalence point, and we're going to be based on the seen endpoint. Endpoint is when the color changes. Right? So how does it work? For example, when you saw in other pages, right, you saw about neutralization. That you saw a strong base, a strong acid making salt and water. And in also titrations, we also have some reaction. In some titration, going to be a neutralization reactions. So, for example, here, how you use the titration to find the concentration. So first, you are going, so let's say, here's the burette, right? The burette here. And you are going, so here. We are going to let drop by drop, slowly drop until the color changes. When the color changes, we are going to get note what was the initial volume and what was the final volume. We are going to use this volume to do your calculation. The volume that was dropped in the LMIR is what you need to know here. So first, we need to use the molarity of the solution that we know, the concentration that will be the standard solution, and use the volume from the burette that we're going to use to find the moles of the standard solution, right? So what's molarity? Molarity is what? Moles divided by volume, right? So you can, if you rearrange it here, your moles is mass multiplied by volume, is what's saying here. So we can use volume and molarity to find the moles. The moles of the standard solution. The moles of the solute in the standard solution. And in that titration, you have your reaction happening there, right? And you use the coefficient from the balance equation that are going to be in the titration. We are going to convert from moles of the solute that we know the concentration to the moles of the solute that you do not know the concentration yet. So we find the moles of the solution that now we know this multiplication, right? Now you know how many moles of the unknown you have. And using the volume that was in the LMIR here, the volume, right? Now you have moles of the unknown divided by the volume that was in the Erlenmeyer, right? Now you can find what? The molarity. So molarity is moles divided by volume. For example, here, one commercial method used to peel potatoes is to soak them in a sodium hydroxide solution for a short time. Then remove them and spray off the peel. The sodium hydroxide concentration is usually from 3 to 6 molar. And the solution must be analyzed pretty often. In one such analysis, we have, in one of the titration here, so in that case here, the burette had the solution here, sulfuric acid. And the volume we spent was 45.7 milliliters of sulfuric acid. So it is these numbers here, these values here, right, was required to neutralize 20 milliliters of sodium hydroxide solution. So what's the concentration of the sodium hydroxide solution? So here is your unknown, right? The reaction is sodium hydroxide and sulfuric acid, right? We have a strong base, strong acid will make salt and water. So let's balance it first, right? Initially, just one sodium hydroxide, sodium. You have 2 sodiums, so make sure you add 2 here. And now count the amount of hydrogen. 2 hydrogens plus 2, 4. And here, you add number 2 here to make 2 times 2, 4 hydrogen. Okay. Right? So what we need to do first here, find the moles number of the solution that you know the concentration. That's the sulfuric acid solution. So we have 0.500 molar times 45 milliliters in liters divided by 1,000. So you found out that you have 0.0229 moles of sulfuric acid from this math here. So the first step, so now you are right here, moles of the standard solution. Now let's convert it sulfuric acid to sodium hydroxide. So what I'm going to convert from one substance to another in a reaction is when you use the coefficients from the balanced chemical equation. Let's go to the equation here. So you have 0.0229 moles of sulfuric acid, right? Right here. And what's the mole ratio that you have here? So sulfuric acid just have one sulfuric acid here, right? Sodium hydroxide, you have 2 moles, so the ratio is 2:1. So we're going to multiply the moles of sulfuric acid to the mole ratio to find the moles of sodium hydroxide. So you cancel out this and this, so you have the moles of sodium hydroxide. So now that you have the moles of sodium hydroxide, that was right here, we are going to use the volume that was in the sample, that is here, 20 milliliters, right? Need to remember, divided by 1,000 here. Convert to liters will be 0.022 liters, right? So molarity is moles divided by volume in liters. So take the moles calculated here, divide the volume that was given, but divided by 1,000. Then finally, you find the molarity of the unknown solution. That is here, 2.29 molar or mole per liter. Don't forget the units and do not forget to count the number of significant figures, right? 3, 3, 3, and way here, your answer should have 3 significant figures, right? Okay, that's the end of chapter 4.